Okay, so welcome everyone to this second day of this program. So we have Professor Yannick Sire from the Johns Hopkins University. So Yannick is also one of the organizers of this program, and he's also supposed to be here. Unfortunately, he could not come. So he's giving this series of lectures online. So Yannick's research interests are in various aspects of partial differential equation, geometric analysis, harmonic analysis, and various other topics. So he has made significant contributions in many of these areas, and he was awarded many awards. And one of the notable things is he's a fellow of the American Mathematical Society. So today he's going to speak on some topics in harmonic mappings with free boundaries and their heat flows. Over to you, Yannick.
Well, thanks a lot. Everybody, the sound is okay? Right? I hope the sound so yeah, I apologize for not being there. Yeah, I would have liked very much to come, but there have been some unexpected obstacles, and so I'm going to try to give this. So it's going to be mainly somehow introductory, and I will just try to discuss several topics related to some recent aspects of the theory of harmonic mappings, and in particular, within the framework of harmonic mappings, ones with free boundary, which are not free boundary in the Caffarelli sense or in the classical PD sense, but more in a geometric sense. And so I will try to explain that. So basically, I would like to so these are somehow the plan, the schedule of my lecture. So first, I will discuss the case of standard harmonic map. By standard, I mean the classical ones going back to decades ago. And so and what I will emphasize mainly is regularity. And then I would like to introduce harmonic map with free boundary and also discuss their regularity, or at least what seems to be known and not known at the moment. And then I would like to squeeze in this type of topic of harmonic map with free boundary, like a class of maps which are rising actually looking. So this is a subclass of harmonic map with free boundary, but they arise, a special class of harmonic map with free boundary, but they arise as some sort of boundary formulation of this special class of harmonic map with free boundary, and basically the use of all the techniques developed in the last 20, let's say 20 years around Caffarelli and all it's been spreading all over areas to deal with integral equations, somehow allow to give a new point of view on these harmonic maps, and this is what I would like to discuss. And I will try to finish by a more technical aspect related to some partial regularity around these different heat flows that you can cook up for this various kind of equivalent formulation at the elliptic level, at the stationary level, equivalent to some extent, but which exhibit very different features for the flow, depending on somehow where you put the time derivative. So which type of gradient flow you are considering. And yeah, so basically, well, harmonic maps, it's a very old topic. It probably goes back to the Plateau problem. So it's a very old topic in geometric analysis or in analysis. And there are several ways to kind of introduce them somehow. So let me try to do to introduce them analytically. So basically, everybody in this audience know what is an harmonic function even on a manifold. And here, and we know a lot of things about harmonic functions. And here, what you would like to understand are So by harmonic function, I mean a function which is satisfying Laplace u equal to 0, but for a function which is from a manifold into Rn, possibly, so component-wise, or R, okay, real valued. So of course, like when you are scalar like a vector valued, if you are Euclidean in Rn, nothing happens. Okay, if you want to look at harmonic map, but there is a case where like you have some sort of nonlinear version of being harmonic whenever like you force the image of the map to be in a manifold. So this is like so you take two closed smooth Riemannian manifold. So by closed I mean like compact without boundary, and sorry. And you consider a map from M into N. Okay, so like this is a well-defined a priori like map as it is, and if you so there is a way somehow an intrinsic way to define what would be an energy associated to this map, so something which would replace the Dirichlet energy for this for the standard Dirichlet energy whenever you are looking at harmonic functions. Okay. So this is what I will try to explain now, like how to define this Dirichlet energy. So assume that everything is nice. Okay. So if you have this map from M into N, like naturally it induces at the level of the tangent bundles a differential du, and it's naturally like this u here should be f, okay, or vice versa. So it's naturally defined by just coordinates, okay. And of course, if now you take the tangent bundle on Tn and you put it back by u, this map U also allows you somehow to define a vector bundle U star Tn over the manifold M. Okay, so all of this is just like kind of you see it like there is nothing here behind, but just classical geometry. And so if you have like a connection, I mean, if you are on the tangent bundle, you can take a connection inherited from the Levi-Civita connection and defining in the most natural way what would be like a density, so the square of du, right? And so it coordinates. It would have like this nasty expression, okay? So you have to work a little bit more to be able to do all these identification. But in any case, if you take a map, nice map from M into N, there is a very natural way to associate a Dirichlet energy to it, okay? By doing this manipulation that I just mentioned, okay? Just because the map induces naturally, like on the bundles, some maps, and you are taking the connection, and then you are like building the density, and then the Dirichlet energy associated to it. Okay. Well, but when you do that, there is one thing that is always hidden to be able to ensure that this construction makes sense is that a chart, you have to send a chart of M into a chart of N, into a coordinate chart of the target. This is to make all this identification meaningful. But the thing is that to ensure such a condition, which is somehow hidden into the construction itself, it requires already continuity of the map U. So you face something that in calculus of variation is a huge problem, is that like you define an energy and you cannot use the Sobolev space H1 right away because you need continuity of the map. So somehow this construction, which a posteriori would make sense if you proved the regularity of the map, somehow like as a drawback, if you don't do something which avoid taking somehow these bundle identifications. So to overcome this issue, and in particular, to be able to write then an Euler-Lagrange equation, because you want to take the first variation, what you do is that you embed, by Nash embedding, you embed isometrically the manifold capital N into an Euclidean space Rk, where k can be large. And so basically, instead of having a map from M into N, you are looking at a map from M into an Euclidean space respect to this constraint that U of X is staying in M almost everywhere in the domain. So naturally, you can define through this embedding, okay, you can define the Sobolev space H1 from M into N. Okay, does it make sense? And so now, if you have like a decent Sobolev space, not very naturally, you have a decent Dirichlet energy, which is defined on the space H1, a Sobolev space, and then you can start doing calculus of variations. Okay? So somehow, like this is the first, the first step that one needs to be sure of is that indeed, the Dirichlet energy is defined somehow through this embedding. Okay. At least, like for the way I want to consider the problem. So of course, like here, like the embedding, the Nash embedding from so the target, right, here into the big Euclidean space comes with an embedding, okay, by definition. And then you can check that formally, if you take like a first variation of this energy, okay, so you take a perturbation, an exterior perturbation, okay, so imagine that you take like a perturbation so that like you keep the constraint of staying in N, so you have to always do variations which are like keeping the constraint, of course. Then you end up like at least like variationally with this Euler-Lagrange equation. Okay, so here what I wrote is the Euler-Lagrange equation in general form. So involving the way you embed the manifold N. So A of U is so it's the second fundamental form at the point U of X, which is a point in the target, a point in N of the embedding into this Euclidean space. Okay. So, okay, so it seems to be like a weird equation. Well, it is a weird equation. But of course, like one has to be like, so the whole point is that if you were harmonic, okay, so this embedding is trivial. Imagine that you are, N is an Euclidean space, this embedding is trivial, you have an harmonic function, right? Now, like this embedding, which is capturing the constraint of staying in the target, okay, so it's non-trivial, and you have an equation by kind of writing down, like doing an exterior variation of your Dirichlet energy, okay? Any question, or is it clear for the moment? So it has to, okay, so it's kind of like a weird looking equation. So let's take examples, it's much better. So let's take first M to be S1, okay? So you are starting with a map, which is, with a map from S1 into any closed manifold N, and you are looking at this energy. Now the energy is only on the circle, okay? And then what you get is actually like when you write down the equation, because of course the second fundamental form depends on all the Christoffel symbol, right, of the manifold N that is now seen as sitting in an RK, right, in a big Euclidean space, large dimension. And what you can see is that, if you take the domain to be one-dimensional, what you are looking, these maps corresponding to such critical point of this energy are actually geodesics, like a parametrization of geodesics into the domain, into the manifold capital N. Okay, so this is, if you look at what is a geodesic, the equation of geodesic, respect to the metric in the domain, right? In the target, sorry, and you are trying to find a parametrization of them, what you get is exactly the equation stars that I wrote here, but whenever the domain is a circle. Or one-dimensional, it can be also just a straight line, an interval, sorry. Okay, here because I'm taking the circle because I'm considering closed manifold. Okay. Well, there is another case which is easy to see, and actually this is what I will be mainly considering somehow, is whenever n, the target is a sphere, an Euclidean sphere. Then the equation is very simple. You see, it's this equation, Laplace u plus gradient u square u. Okay, this term here, gradient u square u, corresponds to the Nash embedding. Okay, so of course, the sphere, you don't need to use Nash, right? The sphere, you just see the sphere Sm-1 as a hypersurface in Rm, and you use what this means to be the sphere, that, and you really do somehow hands-on computations, right? Like direct computation, you don't need to invoke Nash, okay? So maybe let me show you. So there are several features of this equation that I will emphasize, but maybe let me derive for you this equation in a kind of calculus of variation way. So without using the geometry. Okay, so I want to derive for you like this. I want to explain you why, the fact of considering an H1 map, like a critical point of the Dirichlet energy, whenever you start from a manifold M into an Euclidean sphere, why the equation has to be of this form, okay? And here, of course, the operators acting on, these are with respect to the metric on M, okay? But you can take, yeah. Okay, so let's see. So what does it mean for my Dirichlet energy? This means that I'm looking at a map, because I'm targeting to the sphere, I'm looking at a map which is satisfying for almost every x, u square equal to 1, right? This is because I parameterize the sphere like this, okay? And, well, okay, it's going to be a critical point of this energy. So, my Sobolev space is a natural one, so the one so u from H1 of M into Rm, where M is a space in which my sphere is shading, so that u of x is in Sm-1 almost everywhere, which means that modulus of u of x is equal to 1, okay? So this is the setting, and I want to have a look at what is the Euler-Lagrange equation. Formally, what such a critical point would a critical point of this energy, with respect always to this constraint, would look like. So if you look at first order optimization condition, right? You are trying, so first order tells you that you have to be a critical point, okay, of this energy, okay, and since you have a constraint, you have a Lagrange multiplier, and with the Lagrange multiplier lambda comes the first variation of the constraint manifold with respect to u. These are gradients with respect to u, okay, so kind of Fréchet derivatives, and of course you always keep the constraint. Okay, so this is just the first order condition of being a critical point on the constraint, right? Okay, so if you write it down, okay, this is exactly component-wise. Every j is a component, okay, like in the target, okay? So uj the vector u is as component u1 um, okay, because you are like u is the target is Sm. Okay, but of course the whole point is what is the Lagrange multiplier, because of course it depends on the u itself. Okay, so then in the case of the sphere you can do very easy manipulation. So for example, let's take the Laplacian. Okay, now it's another Laplacian, it's scalar Laplacian of the constraint. Okay, if you do that, actually, you get, by a direct computation, you get that Laplace of u squared equal to 0, of course. And when you express what this means and you use again the equation, you see that lambda has to be gradient u squared. This is just quick algebra. Okay. And so at least like for the case of the sphere, when the target is the sphere, which is somehow like a very important case because it already contains a lot of interesting problems. Okay, like the equation at least is has a very specific form. Okay, so let me discuss a little bit the features of this equation. So if you have a to be 0, okay, so if you have an harmonic function, so basically there is no constraint, n is in this case n is the Euclidean space, then you know very well that even if you start with a distribution, I mean, you're harmonic in a distributional sense, the Veil theorem tells you that you're going to be like C infinity right away. Okay, so you have like automatically a very nice regularization of the Laplacian. But of course, here now your equation is nonlinear, okay? But it's even worse because the equation is critical, because if you scale u, okay, and you consider u of lambda of epsilon x, here you're going to have like the Laplacian, you will pay epsilon square, and the fact that you have gradient u square, you're going to pay also epsilon square. So this means somehow this equation, which is now actually a system, because it has to be interpreted component-wise, which is a system, is actually, the two terms are like the size is the same. Okay? And in particular, if you look at an approach by the calculus of variations, okay, so imagine that you come back to this energy here, 1/2 of this energy that I wrote here. You take a domain, you take a compatible boundary condition, and you apply like a direct method of the calculus of variations, right? So what you would produce, okay, is an H1 solution, okay? Like a weak solution of my functional, right? Well, the thing is that if you have an H1 solution, in which space is my right-hand side here? Well, if you have an H1 solution, U is always bounded, right? Because norm of U is equal to 1. And gradient U squared, if you are H1, is only L1. Okay? So it's a big issue because it tells you in particular that if you are only L1, it tells you that out of the equation, at least without doing nothing special, you are borderline for the regularity theory, right? Like you don't want to have Laplace U in L1 because you don't know how to do anything with it. Calderon-Zygmunt theory tells you that you know how to do things only when Laplace U is in LP for P away from 1. So somehow, like at least like at the level, if you take a weak solution, okay, or like even a minimizing at least, but if you are minimizing, you would get like more information. But if you take a weak solution, right, a weak solution of the Euler-Lagrange equation, then this term a priori is a problem. Okay. And one of the issues is that, like, indeed, it's a critical term, like it has the same size, if you want, as the Laplacian. So, but then Okay, so then it's a major issue because initially I wanted to have a nonlinear version of being harmonic if you want, but here like this nonlinear version is so bad that I'm creating an equation which is, well, first this is a system, okay, so I don't have the Georgi-Nash-Moser so it's a system, okay? So, and also like I have this term which has L1 a priori just L1 integrability. So somehow I need to do like something more to be able to move away from this L1 if I can. Okay, but of course you might argue that here I computed this right-hand side for the sphere. Okay, in particular, here, if I come back to the geometric equation, if you go back after my comments here, if you go back to the geometric equation, you see also like, so the Nash embedding, U is always bounded, right? Because this is like constrained to a manifold which is closed. And this is smooth, and A of U capture, like, of course, the embedding, but you still have this quadratic growth in the gradient, okay? So this criticality, you still have it. However, you can hope that the geometry somehow of the target or some specific conditions of the target maybe can ensure that you manage to get like something better than somehow this equation, and in particular, like this is what's going to be happening. So somehow there is an easy case of the regularity theory is when the target n is negatively curved. So when all the sectional curvature of n are negative, not positive. So of course, like I mean, it's not easy, and it's not completely obvious to see from directly from this A of U, but actually, like somehow here, like you have this general. I mean, it's here like the fact that in the case of the sphere that you cannot rule out. Okay, you are not negatively curved, of course. And so in the case of the sphere, you have this equation, okay, and okay, let me show you how the geometry of the target is coming. Well, one possible way to prove regularity, right? So I have to move from L1, okay. So one way would be to get like higher order bounds. Okay, so to get a Lipschitz bound. If I could get a Lipschitz bound, then I would be done, right? Because an a priori Lipschitz bound, because I would have linearized my equation, if you want, right? Somehow. So I would be done, like even if I produce a minimizing solution, like a weak solution is gonna get like a good regularity. Okay, so one way in geometry to prove this type of gradient bounds. So in analysis, what you would do is you try to get an equation for gradient U square. But if you want to prove a Lipschitz bound, right? So you want to get an equation for gradient Q square, okay? Or you hope to have an inequation which is a correct sign for gradient Q square, and being able to prove like by maximum principle, for instance, okay? Well, in geometry, what you do is you get a Bochner formula. So basically, the Bochner formula is, so the classical Bochner formula is when you take n to be scalar valued, for example, and you try to look at an equation for Laplace of gradient U square. So here, what I wrote here, which is the density. Where did I write it? Here. Okay, which is just gradient U square. Okay, or up to a half. Okay, so the thing here, like, is that necessarily the Bochner formula has to you need to have two things, right? When you do this type of computation, you need to see the curvature in the domain, and you need to see the curvature in the target. And hopefully, you need to have both of them going in the right direction. Okay? And so this is what happens here. Because if you are negatively curved, when you write, you can write a general Bochner formula for the density, okay, which has been derived by Hills and Sampson which is the first paper of the 50s, where they look at harmonic mappings between general manifolds, and they derived exactly this Bochner formula. So what you see is that you have a Hessian term here, and here you have like a first term, which is having the curvature, the Ricci curvature of the domain, and here the full Riemann curvature up to some identifications, which are not important, of the target. The thing is that if you use this Bochner formula, you can see that you can prove the following theorem, is that if I give you an harmonic function such that between two manifolds, such that the target has all the sectional curvature, okay, non-positive, then actually this harmonic function is C2 alpha and even C infinity. Okay? Okay, so let me explain you how to prove that. Okay, first let me make a remark is that obviously this doesn't cover this case, okay? The case of the sphere. Sphere is not negatively curved. So let me prove you how to, let me give you a hint on how to prove that. Well, the Bochner formula gives you because so first, okay, this is like a regularity result, okay? So you can forget, you can take M to be flat, okay? Like a domain with a Euclidean metric, okay? So that like this term here disappears. Then this term in the Bochner formula here is of course positive. And if you look at the signs that you have to be correct, but you see that the density happens to be subharmonic. And the thing is that, so you have the correct sign, and this constant here is just the negativity of the Ricci tensor. Okay? Because, no, wait. Oh, yeah. So this term here, like it's going to give you like yeah. This term, sorry, will disappear, and this term will come with the correct sign, provided Ricci is positive. Okay, so this term will disappear because it's positive because you are negatively curved. Okay, in the target, and this term here comes with if you are flat, it comes with C equal to 0. Okay, so you're going to be subharmonic. Okay, so you can apply in particular Moser iteration. Okay, it gives you that the soup, if you are subharmonic, the soup is bounded by an L1 norm in the bigger ball. Okay, but this L1 norm, the L1 norm of the density is the energy, right? So you have an a priori Lipschitz bound. Okay. And if you have an a priori Lipschitz bound, then you are almost done, because then somehow you can come back to the equation here. Then it tells you not only UH1, but Lipschitz as well. Okay. And then you can use elliptic theory, elliptic regularity to bootstrap. Is it clear, or should I explain more how to get by doing the bootstrap? Okay, so basically, like whenever you are negatively curved, somehow the geometry allows you to prove that the density has some good a priori bound, which gives you a Lipschitz control. So gradient Q will be bounded. Okay. So of course, like then you moved away completely from the thing of being L1, because as soon as you are negative, Bogner formula gives you automatically that you are Lipschitz, right? So you don't care about what I said about sorry, you don't care about what I said about like constructing a solution such that this term here scales the same as the Laplacian. Somehow the geometry of the target, the fact that you are negatively curved, gives you automatically a Lipschitz bound. Okay, so this is the part of the regularity which is easy somehow. Okay? Okay? So somehow, like in particular, it doesn't cover the case of the sphere, right? Because the sphere is not negatively curved. All right? So you can relax a little bit the negative curvature. You can assume things on instead, you can have a little bit of positive curvature, provided the universal cover has some good property, but let's forget for the moment this. So somehow, like the conclusion is, if you consider an harmonic mapping which is between two manifolds and the target is negatively curved in some rather strong sense, okay? All the sectional curvature are not positive. Then somehow you produce by minimization, then somehow like the regularity issue at least is not an issue, right? Because like the argument that I gave you based on Bogner formula automatically gives you Lipschitz bound. And this is really because you have the correct sign. If you don't have the correct sign, if you are positively curved, then you have a term with a Laplacian that you cannot control by Moser. So you will not get a Lipschitz bound out of it. Okay? And actually, like yeah, like this is not the way that you prove regularity whenever like you are positively curved, whenever you have the wrong sign here. Okay. All right. So somehow at least it settles completely the case of negatively curved targets. At least as far as like the regularity is concerned. Now, like, what about the sphere? Well, the case of the sphere is an issue, and this you can see it even on an example. If you take x over mod x, okay, it's a map clearly from Rm minus a point, minus the origin into the sphere. And you can see that for n equal to bigger or equal to 3, it satisfies this equation here. It has finite, you can check that it has finite Sobolev norm, Sobolev energy, if you restrict, for example, to the ball of radius 1. However, clearly it has a singularity at the origin. Okay, so this x over mod x is like an example, okay, where actually you don't have regularity, right? Because this is like a weak equation. This is a weak solution of the equation, okay, and which has finite energy if you localize properly, and nevertheless, it has like a discontinuity at 0. Okay. Is there any question? So the case of the sphere, like just this example shows that the case of the sphere is an issue, okay? In the sense that this vortex x over mod x is somehow like you have it floating around, and if you want to prove regularity, so if you want to prove continuity and then more possibly, you need to somehow find a way to rule it out. And actually, this is even worse because uh, you can prove. So let me. So this is even worse because the only place where you will have where you will have full regularity is the case of surfaces. So let me maybe like move to my tablet. Can I? Yeah. Whiteboards. Do you see it? It's okay, or do you see the whiteboard?
Yes.
Yes. Oh, I have a question in the chat. Like, what about the condition? You need to have. You can allow some positivity. At least with this argument, you cannot allow some negative. Some all the sectional curvatures have to be negative. With these arguments, you can modify the argument a little bit, and the condition is that the universal cover of the target admits a convex function which has quadratic growth. So which is kind of covering a little bit of positive curvature, but not too much. With this argument of Bochner, you cannot use, you have to modify it you cannot allow some positive sectional curvatures. Okay. Okay, so if you see it, maybe I should, can I don't know if I can, let me see. If I can move it. Do you see well the screen or not? Maybe I can expand it, no? The whiteboard. Okay, so, okay, oops. Nope, why? It doesn't work. Ugh. Oh. Oh, okay, good. Okay, so I have, okay, so sorry already. So let me come back to my, let me come back to my equation. Okay. Yep. Okay. Okay. What? I don't know. What? Okay. There you go. Let me come back to my equation. So you want to, I want to show you a little bit what is known whenever you consider this type of equation. Okay, so basically U here is from a manifold, let me call it sigma, into my target N. Okay, so what happens is the following. So using this kind of canonical function u of x equal to x over mod x, Rivière proved that you can construct a solution, a weak solution of this equation, which happens to be discontinuous everywhere. Okay, let me put a minus here. Okay, so Rivière, okay, Tristan Rivière proved that there is a solution, a weak solution of this equation, okay, from the 3-ball into the 2-sphere, okay, so a very special weak solution, which is made up of all these kind of dipoles, x over mod x, which is discontinuous everywhere. So the situation is even worse than my example, because this example tells me, okay, it's a weak solution, but it's continuous only at 0, right? No, actually, you can make, if I give you a whole ball, you can fill it with completely with a solution of this equation, okay, a weak solution of this equation, which is discontinuous at everywhere. So this is like a problem, okay? So it tells you that the best case scenario when you are in 3 dimensions and higher is you cannot have full regularity of a weak solution. It's impossible because of this example by Rivière. So you might ask, like, well, so then if you don't have full regularity, at least you can hope maybe to have partial regularity. So you want to prove that you don't have a weak solution over all you don't have a regularity over all the domain, but on on the complement of a closed set of the domain. Okay, which is like the typical partial regularity that you can hope in general. Okay, I remind you that these are vector valued, these are systems. So there is no Nash theorem and this type of thing. For system, it's only for scalar values that you have the Georgi-Nash model, right? But remains the case of 2 dimensions, right? For 2 dimensions, Rivière, like a theorem, tells you that you have like a completely discontinuous solution, only dimension 3 and higher. What about in 2 dimensions? Well, in 2 dimensions, actually, like the situation is drastically different. You do have like actually full regularity. So I will discuss probably next time the case of regularity in 2D. But let me just make a summary of what I just said. Okay, so you take a map which is from M into even a sphere. Okay, and the dimension of the target of the the dimension, okay, of the domain is if n is bigger or equal to 3, okay, there exists a weak solution which is discontinuous everywhere, okay, on the whole B3 for 3-ball, for example. So in dimension higher than 3 and higher, okay, in general, the best you can hope is partial regularity. However, what you can prove is the following. So this is a result by Hélin, that if the dimension is 2, okay, so this means that this map here starts from a surface, and actually you can take any target, not only the sphere. It works also for any target, but let's take the sphere. Then any weak solution, so an H1 block, for instance, solution is C infinity. Okay? So Hélin proved that this counterexample of Rivière to regularity occurs only dimension 3 and higher. Okay? In dimension 2, if I give you any surface and I take the target to be a sphere, but actually, like what you can prove is that it works for any manifold, okay, in the target, any closed manifold. Hélin tells me that any weak solution of my harmonic map equation happens to be smooth, okay? Provide C infinity, I mean, here you have as much smoothness as you want, depending on the smoothness of the manifold M, okay? So it has to be understood this way. Okay? So there is a really, like in the case of harmonic maps, there is really like a difference between 2 and higher. And this is not a Sobolev embedding. This is not because of a phenomenon like Sobolev embedding, or this is really the fact that the harmonic map equation that I wrote before, okay, so let me open a new page. So let me let me clear the page. The harmonic map equation has a very special structure that I will explain next time tomorrow. But the harmonic map equation, this nonlinearity here has a very special structure. And what Alain used to prove his theorem is that the algebra behind this harmonic map equation, so the algebra behind the structure of this term is so special that it has like a structure which allows you to prove that you have a compensation, a higher integrability somehow for free. I mean, for free in the sense that up to like, because you know how to like for free in the sense that it comes really from the structure itself of the equation. Okay? So it's a really like a big feature, big difference between 2 dimensions and higher. Okay. So the whole point of harmonic maps are actually somehow to design, to understand, I mean, the whole point, at least at the regularity level, is to understand which type of phenomenon do you have, okay, in which dimension, because really like there are strong differences between 2 dimensions and a higher dimension. Okay. Is there any question? So somehow, like the whole goal of these lectures is to understand all these topics revolving around the structure of such systems. This is what I want to address. Okay. But somehow I left open the existence part. Okay. Why? Well, because I kind of like put it under the rug, because uh, when I was like trying to when I was let me come back to okay. Uh, Let me come back to my slides. When I was like discussing the case of negative target, I was really like because I wanted to kind of discuss really like the regularity. Once I have like a decent energy, decent in the sense that it's well defined, then I can use the calculus of variation tricks, right, to to prove that I can produce a solution by minimization, right? But if you have a solution by minimization, it's this means that you are taking a boundary value problem, right? Because otherwise you cannot apply standard calculus of variations, right? But originally my problem M is without boundary, right? M is just a closed manifold with compact without boundary. Okay? So how do you do now to produce a solution when you cannot when you cannot like somehow use like a direct method of calculus of variations, right? Well, so this is what to do that. So let me come back to the tablet. To do that, you have so Hills and Sampson. Like Hills and Sampson, so design a flow. So let me explain. Oops. Okay. So Ilse and Samson in their paper at the Hopkins Journal, the 50s. Actually, these are like the ones who introduce this energy that I described, okay, and looked at the case of negative targets, okay? So let me write it this way. And G is a metric on M, okay? So let me, so now, like what you would like to understand is basically how to build. You have an energy, right? And you would like, which is quadratic, and you would like to build whenever, like, actually, you cannot use the direct method of the calculus of variations. Okay. Well, what they designed is a gradient flow of this energy. So, what is a gradient flow of this energy? If you write the Euler-Lagrange equation, you are deforming. So, okay. So what do I have? Like, see, if I forget like the DTU for the beginning, if I forget the DTU, I have my harmonic map equation. Okay. Here you design a gradient flow, which is a parabolic flow. And you start with an initial, so what they studied is that you start with an initial data you not, sorry, which is of course a map from M into your manifold N, okay? And you ask yourself, can I deform it to an harmonic map from M into N? Okay? This is really like, so one has to imagine that this paper was the 50s. It was before everything. Huh? So they actually like, I think that this is the first paper I'm aware of where they used the parabolic deformation to solve an elliptic equation. Because what they say is the following. So let's take a map from M into N, which is like a smooth, and can I deform it along a flow, along the gradient flow of this energy, so that when t is going to infinity, for instance, then I converge to an harmonic map. So a solution of my stationary equation. Okay? It's clear? So so they actually worked out really the estimates of the flow, and what they prove is that whenever the target is negatively curved, so exactly the same assumption as the ones I described for the elliptic theory, then actually the flow is defined for all times. It doesn't blow up in finite times, and when t is going to infinity, at least along the subsequence, and then it's been improved, you get that you converge to an harmonic map. So basically what Ilse and Samson proved is that whenever all the sectional curvatures are non-positive, actually the flow is smooth, okay, and along a subsequence, it's converging along infinity, going to a Tn going to infinity, it's converging to U infinity, and U infinity is an harmonic mapping. Okay, so doing that, you kind of avoid, like somehow, having to use some minimization argument because you have designed a flow so that like actually which is leading you to the solution of your problem. Okay. Is it clear? So at least like really like in the case of negative targets, like a negatively curved targets, in this case, everything goes well somehow. Okay. At least in this simple setting. simple, at least in this like Riemannian type setting. Okay. So somehow, like really, like the whole problem already in this type of business of harmonic mappings occurs like when the target is even the sphere. Like a lot of the phenomena that you can observe for positively curved are already present when the target is a sphere. So somehow, like what is very important to understand the structure of the solution, but the structure of the flow as well, whenever it's a sphere, okay? Because the theorem that I just stated from Ilse and Samson here, the theorem does not, this theorem is not true if you take the target to be the sphere. It's Ilse and Samson AJM. This is like the famous one of Ilse and Samson. Oops. Ilse and Samson. And this is 50, this is American Journal of Math, the Journal of Hopkins. Okay. And this is the 50s. It's the paper having like, I don't know, thousands of citations. It's easy to find. Okay. So basically, in this paper, the theorem that I just stated and erased is like the fact that you have a globally defined solution, which is nice, no finite time blow-up, and which is converging to infinity, at infinity, to an harmonic map. It happens only in the case where you are negatively curved in the target. So now, if you come back to my problem, like if I take now this flow, so I look at the same deformation, okay? I try to deform, except a map, except that now I want an harmonic map into the sphere. Let me start even with a surface, okay? Then what happens is that, in general, you will have finite time blow-up for this flow. So the situation is really drastically, again, as in the case of the static problem, the situation is drastically different now in terms of the target, okay? And even if you start from a sphere, even if you start from a surface, you still have finite time blow-up. You know, if you remember, like what I mentioned before, I mentioned that if you take an harmonic map from a surface into a sphere, right? This map is always smooth, okay? At least a weak solution of this map is always a weak equation, and each one log of solution of this equation from a surface, so a two-dimensional manifold into a sphere, is always smooth. Here, the flow is not the case. The flow, even if I start from a two-dimensional object, will develop singularities. Okay, so now so this means that there is another thing happening for this system at the level of the parabolic equation. So really, like the only case where like you are really on the safe side is really like when the let me show you the target is negatively curved. This is the only place where everything goes well. Okay. So here I kind of described the basics of the theory, or the easy part of the theory when everything is Riemannian. As you can imagine, one can get much more complicated systems than the one I consider because you can vary the structure for the domain and the structure for the target. Okay, so you could have a look, for example, at hyperbolic spaces, for example, in the domain and in the target. You could have a look at manifold with singularities, both in the domain and the target. And all of these systems have actually like many geometric applications. Okay, so let me finish, let's say, because I think I have like, 10 minutes. Let me finish by saying that, so the way I introduced harmonic maps is a little bit on the cheap side because I just said like, oh, well, I just want like a generalization of being harmonic whenever I put a constraint on which my image has to land for my map. But actually, there are good reasons to look at these objects also geometrically because more things which are more prevalent because in 2 dimensions for the domain, maps can be used to parameterize minimal surfaces in the target. And as I said before, when you are like one dimensional in the domain, the equation is a parametrization. The map is a parametrization of geodesics in the target. Same for in a higher dimension. Okay, in 2 dimensions, if you start from a surface, this is an object which is linked to minimal surfaces sitting in the target. So they can be used as a way to parameterize minimal surfaces. And also, harmonic maps can be used to prove some rigidity. And this is really related to the idea of deforming a map and trying to understand somehow the homotopies sitting between 2 manifolds. So there is a lot of various results that you can prove at different levels, not only between Riemannian manifolds, but you can look at even more complicated structure where the existence of such maps and their possible rigidity in the sense that only, for example, only constant maps can hold in some settings or things like that. This, like exactly as Liouville theorem, have a lot of consequences on the geometry or the topology of the manifold of the domain or the target. And there are still a lot of questions related to the rigidity of different objects. And one way to attack these rigidity issues is to consider harmonic maps between these objects and trying to deform them and trying to understand what is happening to those maps. And the rigidity typically in this type of business, it's always come, at least in some good situation, for Bochner formula. Because the Bochner formula not only gives you an a priori ellipsis bound, but if you integrate it and you can manipulate, I mean, you are able to estimate terms, so, okay, it gives you also the vanishing of this type of quantity, for instance. But this type of quantity vanishing, the fact that the connection of this form du is 0 means that du is parallel. It means that the map is totally geodesic. So, but totally geodesic means that you are sending geodesics from the domain into geodesics of the target. So these are very special maps, right? So the use again of the Bochner formula at the second layer, this is always the way you use Bochner formulas, somehow, is giving you more, like on the manifold, than just the ellipsis bound that I used it for initially. So maybe I should stop here. Thank you very much.
Any questions? Yeah, please.
Hello, Professor. I just wanted to clarify a few things. So one of the exercise you did give was this Laplacian UX is orthogonal to this TUXN.
Yeah.
So what is this object? So Laplacian UX will be an element in the TUXN as a vector?
Yeah. So this is like another way. Let me write it down. Let me show the thing. It was before, right? Yeah. So one way to prove to write this equation, another way, which is a distributional way to write this, is equivalent, if you want. If you have everything smooth, I mean, everything smooth, it's equivalent. Is to write that the Laplacian is actually orthogonal. So to the tangent space at n at the point u of x. So
But
you
as
take
such,
yeah.
yes, this Laplacian U of x, this lies in that tangent space itself, or
No, it
as,
means
as an object, it is lying where Laplacian UX.
yeah. I mean, it's orthogonal, so one has to. There is like a choice to make, huh? But it might be easier to say that Laplace u times like dot phi is equal to 0 for every phi in the tangent.
Okay.
It might be better to write it what I meant that is actually like sometimes this equation is called the distributional version of the. If you take the sphere, for instance, this equation is Laplace u wedge u equal to 0.
Okay.
Right.
Just one more clarification. So this M, we usually take it to be closed, right?
Yeah.
And so if N is non-positive, like the harmonic maps, if it's correct, it's constants, right? These are going to be constant. So like with connection to the suballow space, what is that we are actually looking at? So this function.
So I did okay. That's a good point. So I didn't look at so I didn't talk about this triviality that you are mentioning. Indeed. So what Ilse and Sampson proved is that if M is closed indeed and N is negatively curved, only that the constant maps are they are only constant maps, right? Well, the thing is that I didn't look at this problem in the sense that so it's okay. So of course, if you look at this space, okay. So your question is about
The
what is
connection between this
space,
harmonic
right?
maps and this suballow space. Yes.
Yeah. Okay. Wait. Let me. Yeah, because if you take a map, yeah. So this map, yeah. Of course, now it would be. The thing is that if you are harmonic, even if you are smooth, if you are harmonic, you are smooth, right? So you can forget this Sobolev space, right? Sometimes if you are negatively curved, right? Because you know that any critical point will be right. You apply this result, right? Somehow. What I wanted to say.
Weissenberg, Bochner result.
Yeah. Here. Well, let me see. Yeah, a posteriori, you prove that this map, if it exists, it's the constant. And then indeed your Sobolev space happens to be the trivial space.
But are we interested? But we wanted to reduce regularity in the suballow space, right, sir? Or?
No. What I meant to say here is that I mean this
For this
statement.
theorem. Okay.
I'm taking always an harmonic map, which is not a trivial one, of course, okay? But it's an a priori statement, right? Actually, the statement it's better written that you take a domain, okay, with a flat metric, or B1, okay? You take the ball with a flat metric into N, which is harmonic, and if N is negatively curved, then U is a C2 alpha log. This is a better way to write it, okay? Because here, indeed, if M is closed, the only map you might have is a constant, okay? But this we don't know it a priori yet. Does it make sense?
Yeah. Okay. And just one more thing I kind of missed. I think you mentioned something about for the two-dimension there is full regularity, but for high dimension there is no like Nash embedding analogy.
No. There is no regularity for higher dimension. There is always a Nash. The thing that I am embed is always a target. What I said, like for dimension 3 and higher, you can construct a weak solution of the equation, which is discontinuous everywhere. Okay? So there are some weak solutions. This solution is not minimizing. Okay, it's a weak solution, but it's not a minimum. A minimizer, sorry. It's a weak solution. Okay, so if you want to have more. So if you want to have partial regularity, you need to assume more in the solution than just being weak. However, like if you have a weak solution for the domain which is two-dimensional, then this is smooth.
Okay, so thank you very much.
Okay, any other questions? Okay, so no other questions. So let's thank Yannick once again.
Thanks a lot. Thanks a lot.
Okay,
and,
so thank you, Yannick. See you tomorrow.
And tomorrow I will discuss the regularity of planar maps. Okay, thank you.
Okay.